How you doing? I'm Mr. Rose, and today we're going to continue talking about our DC circuits. Specifically, we're going to start with series and multi-loop circuits. We're going to get to Kirchhoffs Junction law, and then we're going to learn how to sum circuits using both Kirchhoffs loop and Kirchhoffs Junction law. So we know there are two types of circuits. We've spoken at length already about single loop circuits, which essentially is a series circuit, and then we have multi-loop circuits, which are parallel circuits. As a quick review, here's a single loop circuit with a potential difference or an ideal battery, which I've labeled our script E, or current is going around. I've labeled the direction of my direction of my potential difference, and I've labeled the current traveling. If I wanted to traverse around that circuit in order to find its current and its potential difference, I have that E plus my potential difference minus I times R1 minus I times R2 minus I times R3, getting all the way back to the beginning of the battery equals 0. Basically what we're saying and what we're seeing here is that the potential difference applied across every resistor, that potential may be different. However, we should be able to see that the current I, and I in each resistor in a series or a single loop circuit has to be the same. If I sum up all those potentials, I could bring IR1, IR2, IR3 to the other side. I would see that my potential difference is equal to the sum of all of my potentials. So, moving forward, if I am looking, say, for the equivalent resistance for that circuit, for a single loop circuit, what we can see here is 1, 2, 3 resistors there. I've summed into one resistor here, my REQ. Well, here I had my E minus IR1, IR2, IR3 equals 0. That's the same thing now because I have this equivalent resistor REQ. So I would say that my battery minus my current times that equivalent resistance is equal to 0. Again, I could bring that to the other side and we would see that my potential difference E is equal to I times R. It should be very simple to see then that we have my current for my total current here. I is equal to my battery divided by my total resistance. I could do the same thing with my equivalent circuit, where I have I is equal to my potential difference E divided by my equivalent resistance. So in short, to figure out the total or the equivalent resistance for a single loop circuit is just my REQ. We can see that the equivalent resistance is the sum of all of my resistance from I equals 1 to N, as many resistors as I have. This is relatively straightforward. Now, what if I don't traverse the entire circuit? In other words, what if I want to know the potential just between A and B? Well, we're still going to use the same rules as we just applied with that loop rule, except I'm not traversing the whole circuit. So I made some arbitrary values here. We said the EMF is 12 volts. I said that resistor was 4 ohms. And the internal resistance R is just 2 ohms. Now, what if I want to know the potential difference between A and B? So start with A. I'm going to say the potential at A plus, right, we're going to add that E minus I times little r, my internal resistance, equals the potential at B. So I can rearrange and I can say VB minus VA equals E minus I times R, my total current times that internal resistance. Now to evaluate that, I'm going to need to know the current going through it. So now I'm going to apply the loop rule to the entire thing, because we know the current here is also the current through the entire thing. So again, I have my battery minus my internal resistor minus the current traveling through that resistor, the potential through that resistor equals 0. Rearrange, I know the current anywhere, but specifically where I'm looking at, but the current anywhere in this single loop is just the battery divided by my internal resistance R plus the big resistor R. Again, that would be my equivalent resistance if I wanted to try and solve it that way. Combine what I've labeled A and B. We have VA minus my battery equals, that's my current, equals VB. That's what I started with here in purple. Then in black, I have VB minus VA is equal to my potential difference, E minus the current times R. If I plug in the numbers given, I should solve that out to find the potential between A and B is just 8 volts. It's a very simple application, what we've done thus far. Now here I have a multi-loop circuit. We're going to apply the things that we already know. Here I have 2 batteries battery 1, battery 2, and I call them ideal batteries. And the first thing I want to do is I want to add the direction of that potential difference. So those batteries, E1 is going in that direction, E2 is going in that direction, and I'm going to change colors for E2. So let's should do that now. And now I'm going to add my current arrow going around that circle. I'm going to add my current going around that loop. And now I'm going to add my current. So I can see here that I would have I1 over there. And I1 is going into junction D. And I would have a current I2 going through this resistor, I2, and a current going in to junction D there. So I would have current I2 and current I1 traveling up through junction DB. Well, that would lead me to believe that I would say I3 is equal to I2 plus I1. That, in essence, is Kirchhoffs Junction rule. So the junctions I keep talking about are where my circuit connects from two different points. There are three branches. I have branch BAD, I have branch BCD, and then I have branch BD. And the current rule tells me that the sum of the currents entering any branch, so the current entering branch DB has to be equal to the current leaving branch DB. Well, that makes sense. I have I have I1 plus I2 would equal in this branch, grab this marker, I3. So I3 is easily equal to I2 plus I1. Again, this is Kirchhoffs Junction rule. The sum of the currents entering any branch must be equal to the sum of the currents leaving that branch. If I look at D, that's where we can see what we just wrote. Now, Kirchhoffs loop rule and junction rule are how we solve any multi-loop combination. So I'm going to use the junction rule. I have three loops. I have loop BADB, BCDB, and then a big loop, BADCB, the large loop. To figure out if I want to be current 1, current 2, and current 3, I'd apply the loop and the junction rule. So first I did the left loop, starting with E1 minus I1 times R2, that was an R2, minus minus I3 R3 equals 0. Got back to there. Now the second loop, I would have the battery E1 minus I2 R2, come back around minus I3 R2, or I equals 0. And then my big loop, it doesn't matter which one I start with, but make sure your positives and negatives work out. I would have plus E minus I1R going around. Now I'm going against the current, so this would have to be a positive value. Plus I2R2 minus that battery E2 minus E2 has to equal 0. And we'll see that these currents were almost drawn arbitrary. And we're going to see that in our next example. So, to use Kirchhoffs junction and loop rule, here's a more specific example. I have 1, 2, 3 identical resistors, which are R1, all 2 ohms. I have one battery E1, I have one battery E2, and a second battery E2. Now what I did draw is I drew my EMF in the direction of the EMF, because that we know. But I didn't know anything else about this circuit, so I arbitrarily drew current arrows. So I said that current 1 was traversing around this way, and here I have 2 batteries. So I have current 2, I don't really know what's going to happen. So I said current 2 is traversing around in that direction. I'm going to apply the loop rule and the junction rule. Based on my picture, I can see, like I said before, I1 comes into junction A, I2 comes into junction A, therefore, through AB, I3 must be I1 plus I2. So that is applying my junction rule. Now I'm going to apply my loop laws. This left loop, which is here, I'm starting at my battery. That's just always where I start. My battery 1 minus I1 R1, come down, minus, I know I3 is just I1 plus I2, so I sub that in right away. I1 plus I2 times resistor 2 minus, I'm going the wrong direction, so minus my battery minus R1 I1 equals 0. Now I can simplify that out to get, collect terms. I know my total potential, E1 minus E2, is equal to I1 R1 plus, that's I3 R2 plus I1 R1 again. And I'm stuck there. One equation, too many unknowns. Now I go to the right loop. Again, I've already done my junction rule, so looking at my right loop, I have my battery 2, and remember, these two batteries are identical, so that's actually going to help us out. I have battery 2 minus, I'm starting here. Battery 2 minus I2 R1 minus I3, which again is just I1 plus I2. So minus I1 plus I2 times R2 minus my second battery. Again, it's subtracting because I'm going the wrong direction across my battery. Minus I2 R1 equals 0. And here we should see that that and that cancel out. So it was easier to simplify. When I solve, now I have two equations with only two unknowns. When I solve that out, I find that current 1 is equal to negative 0.5 amps. Current 2 is equal to 0.25 amps. Current 3 was equal to negative 0.25 amps. Those negatives are important. What that negative tells us is that the currents we defined, in whatever direction we defined, were actually going the wrong way. So in my picture, I would just redefine my direction. Current 1 is not actually going that way. Current 1, if asked, is actually going in that direction, counterclockwise. And current 3 is not going down, but current 3 is actually going up in that direction. And everything else works out. Again, that's all I have for you today. Thanks for watching. Next time, we're going to tackle finding the equivalent resistance in a parallel circuit along with RC circuits. See you next time.